Let's have a look at how to integrate rational functions by partial fractions. Now, what type of rational functions am I talking about? Well, anything of the form px over qx, where qx and px are some sort of polynomials. So, the first thing you need to do when you encounter a type of question like this is to check to see if p is the higher order polynomial, or the numerator. If it is, you need to perform long division to simplify the fraction, otherwise integration is going to be a problem for you. But if qx is the higher order polynomial, you don't need to perform long division. So let's have a look at an example. As you can see here, the numerator has a higher order polynomial, so we need to perform long division. Now, long division you should have done in a previous course, but essentially all you need to do is divide, see how many times this factor goes into this factor, then put it up the top, and then multiply the rest of the factors, and then subtract this equation from this equation. You keep repeating that until you get 0 or until you can't reduce any further. In that case, this will be your remainder. So after you've performed long division, this is the equation you'll end up with. As you can see, you'll multiply by these two equations, and then you add the remainder. So now our new px qx will just take this form. So once you have made sure that the denominator has the highest degree polynomial, you need to identify what type of rational function you're dealing with, because there can be different types. So you can have one that has distinct linear factors, repeated linear factors, or something with an irreducible factor of degree 2. Now actually, let's represent a fraction that has all three of these cases. So as you can see, this one has a repeated linear factor, and in that case you make as many fractions as the degree of the polynomial. So this has got a second degree, so you need to split it into two and then have separate coefficients for each. Now this one is a distinct linear factor, so it just has its own coefficient, and you match it with the denominator of the distinct linear factor. The third case is the irreducible factor of degree 2. This one has a different numerator. It's not just a single coefficient, it's a linear coefficient, so remember that. And it's the same case as the repeated linear factor for the denominator. You repeat it for the amount of times that there is a power present. So how do we find the coefficients? Let's do an example to demonstrate this. So as you can see, there are no linear factors repeated, and there are no irreducible factors of degree 2, so we have distinct linear factors, which means that we need to split our rational function into these two partial fractions with their own respective coefficients. And so what we now need to do is combine the fractions to equate the denominator. So then what we can do is we can equate the numerator, and then we can find the coefficients. So how do we solve this type of equation? Well, in this case, because it's not too big, we can just get rid of them by making a or b disappear. So letting x equal to 2 will make a disappear so we can find b, and then letting x equal to minus a half will make b disappear so you can find a. And so this will be our partial fraction, and then all we need to do is integrate, and then of course this is just the logarithm. The integral of this is the logarithm, so this would be u prime and this would just be u. So one more example. Let's try integrate this one. Now this is the one that we did long division on, because as you can see, this has a higher degree polynomial than px. The numerator has a higher degree polynomial than px, so we need to perform long division. So as you can see, this is what we did previously, and because we have distinct linear factors, we don't need to do any partial fractions on this part, we just need to do partial fractions on this part because our denominator is larger than our numerator. So we split it, we assign coefficients for each distinct linear factor, we multiply to get the denominator the same, so then we can compare the numerator. And then to find a1 and a2, we let x equal 1 and x equal minus 2 to cancel them out, and then we can find that a1 is minus 1 and a2 is 2. So this is our partial fraction, and then of course the integral of these functions is a logarithm, and there you go. Don't forget to put this back in over here. So what factors does this irrational fraction include? This one's a little different. As you can see, it's got a repeated linear factor and an irreducible factor of degree 2 repeated once. So check to see that qx is indeed larger than px. Need to make sure that this is larger than this one. So when you do this sort of thing, you don't need to go all the way, multiply it all the way. As soon as you see that it has a factor or a polynomial that is larger than the numerator, you're done, you're finished. That's it. So there's no need to do long division here. So now we just need to split our rational function into partial fractions. So we have a repeated linear factor, which means that we need a coefficient for each. Then we have an irreducible factor of degree 2, which has a coefficient, a linear coefficient. So now we need to make all of this into one fraction so that we can equate the numerators. So this is our denominator. So we multiply everything by our denominator. So no matter how large your equation is, the denominator will always be the same as the original function you are integrating, otherwise you can't compare coefficients. So after you've done this, you'll get this long equation. Now in this case, because we have a lot of factors, we're not going to simply let x equal 1 or minus 1 and cancel them out, because we're going to get stuck. So we need to expand our equation and compare the coefficients to the numerator of the function we want to integrate. So as you can see, the expansion process is a bit tedious, but it works. What you'll end up with is this, and then you just compare that this coefficient to this coefficient. So a plus c must equal to 1, and so on. And then what you do is, once you have your equations, you need to think if you need to use Gauss-Jordan elimination. Do you have a lot of linear equations? Can you knock them out? So scan your SLE and see if you can knock out any coefficients. And in this case, luckily we can. We don't need to do some Gauss-Jordan elimination. So as we do this, we find c equals 1, a equals 0, d is 5 over 2, and b is 5 over 2. Now we just substitute all of those coefficients into our equation, and we find that the first integral disappears, and this one will split into 2, because integrating that's going to be a bit of a headache. Another thing is that the second integral will also be difficult to integrate unless we can make the numerator a derivative of the denominator, because as you can see in this case, this is just the chain rule because it's enclosed by a polynomial, whereas this is not, it's in 2 parts, so this is a different case of function. So what we can do is multiply by 1, but make this 1 2 over 2, so this can be 2x over x squared plus 1. So now when we integrate this, we'll get a logarithm. So after we've split our function into 2, as we have done here, we can then integrate. And what I like to do is to make this fraction into just a -2, so I can, when I integrate it, I decrease the power and divide by the new power. It's much easier to do on paper than in my head. And that's it. Once you've integrated, you are done. And yeah, you may have to look into your formula sheet for x squared plus 1 to find the integral of that, which is just tan -1x plus c. And that is it. So you learned how to integrate a rational fraction by partial fractions. And there are 3 cases you need to be aware of: repeated linear factor, distinct linear factor, and irreducible factor of degree 2. You learnt some techniques on how to find coefficients, and you learnt some tricks on what to look out for when you get to the integration stage. Archimedes would be proud of you. Well done. So integration topics that I've covered so far are the following, and I've just got one more to do on integration by parts. So feel free to watch these other videos, and good luck for your test.